Hi. Hi. In this section, let's talk about the well-ordering principle. This is a second section. Section 1.2. Well-ordering principle. Basically, we're trying to talk about the n, the set n. You see, so far we have the set of natural numbers, the set of all integers, the set of all rational numbers, and the set of all r. N is different from other threes because n, every subset of n has a minimum number. You can think about it. Only n, the subset n, has a minimum number. Z, Q, R, not every subset has a minimum number, right? And when you have minimum number, basically you have a direction. It's like the opening. It is always open to the right or open to the left. Okay, so let's start the discussion. So first, let's discuss what is a minimum. Definition. A number x is a least element of a set E in a subset of R, the subset of R, if and only if x belong to this set and x is less than or equal to a for all a in E. So it's an element. It is less than or equal to any other element from this set. Then it is called a least element. Okay. Okay, after we have the definition of a least element, let's see the postulate. Postulate 3 is called well-ordering principle. Well-ordering principle states every non-empty subset of n, the set of natural numbers, has a least element. So this is a postulate axiom. You don't prove it. It's one of a property, essential property. Okay? So this well-ordering principle only works for the set of natural numbers. So this principle is not satisfied, is not satisfied by Z, Q, and R. Okay? Because you can always find a subset such that that set does not have a least element. Okay, that's easy because you can just pick up itself. This set does not have a every set is a subset of itself. So this set itself does not have a least element. And because of this well-ordering principle, remember we mentioned the principle of mathematical induction. The theory behind the principle of mathematical induction is this well-ordering principle. We have an application of the well-ordering principle. It is a so-called the principle of mathematical induction. The principle of mathematical induction. Well, let's see how we get this application. Whenever we say application, basically we say we can prove it. We can prove the principle of mathematical induction. This principle is a postulate you do not prove. The principle of mathematical induction is something you can prove based on this postulate. Theorem. Suppose for each n in set n that A of n is a proposition that satisfies the following two properties. Okay, property 1, when n is equal to 1, A of 1 is true. You're going to verify this. Prop 2, for every k in n for which A of k is true, A of k plus 1 is also true. Okay, so it's like the domino. You push, the first one is pushed. If any two elements are close to each other, AK AK falls, next one will fall, then A of n is true for all n belong to the natural numbers. Okay. Okay, let's try to prove why this makes sense. Why it is correct. You're going to show A of n is true for every natural numbers. Now let's suppose that this principle of mathematical induction is not correct. The theorem is false. If you assume the theorem is false, so basically you satisfy two conditions, but still the statement is not correct. It means for some n in n, A of n is not true. The statement says for all n it is true, but here if you want to get a negative statement, just means you can find some integer natural number n so that A of n is not correct. Then the set E, which is a collection of a natural number n, so that A of n is not true, is false. Then this set is non-empty, right? Because you already know that for some n this is not correct, it's not true, it's false, then this set of the indices, false statement, this index set is not empty. If it is not empty, by the well-ordering postulate, by postulate 3. E has a least element. Let's call it, say, X. It's a subset of natural numbers. So by the well-ordering principle, this subset must have one least element. One least element. Correct? And we call this least element X. Okay, we call it X. So here, it's least element, so X belongs to E. A of X is false. X belongs to E just means A of X is false. But we know that this theorem, the first two, those two conditions are examined. A of 1 is true. A of 1 is true. So X cannot be 1. Here you assume A of X is false, but we know A of 1 is true, so X cannot be 1. X is not a 1. Remember that we know for the natural numbers, if it's not a 1, then X minus 1 belongs to the natural numbers. X minus 1 belongs to the natural, right? Only for 1, you subtract 1, it does not belong to the natural numbers. Okay, then, and we know that X minus 1 is strictly less than X. X minus 1 is strictly less than X. And X is a least element of E. So what we can say? We see that A of X minus 1 is true. A of X minus 1 is true. If A of X minus 1 is false, then it will contradict to the situation X is the least element, because X minus 1 belong to E and X minus 1 will be less than X. That's wrong. That contradicts to the statement, to your assumption. Okay? So it's because X minus 1 does not belong to E. Not belong to E, A of X minus 1 is correct. Then by the second condition, second condition says A of X minus 1 is true, then A of X is true. You stand at the index X minus 1, you know that the statement is correct. Then you jump one step, the next term should be also a correct statement. X minus 1 and plus 1 is AX. But here, this contradicts to the situation that X belong to E. X belong to E, A of X is false. Okay, so you go whatever direction, you always get the contradiction. Hence, your statement is incorrect. You suppose the theorem is false, hence the theorem is true. In other words, this E must be empty. It cannot be non-empty. If it's non-empty, it will always have a least element. If it is empty, there's no least element. But when E is empty, A of n is true for all n. Hence, A of n is true for all n in n. Right? So this is a proof. We still prove it by contradiction. Right? But here we prove the principle of mathematical induction by the postulate well-ordering principle. They are both called principle, but one is axiom, the other one is a theorem. Okay? Okay, now let's use this principle of mathematical induction to prove something. Okay. 1.12 example. Prove that sigma k from 1 to n, 3k minus 1, 3k plus 2 is equal to 3n cubed, 6n squared, and plus n. For all n. For all n. Well, let's see the proof. Okay, so first we examine the case for n equal to 1. Before that, let's give the name. Let a of n represent the statement k equal to 1 to n, 3k minus 1, 3k plus 2, the 3n cubed, 6n squared plus n. Okay, so when n is 1, for n equal to 1, the left hand side, n is equal to 1, you don't have sigma, you just have one element. So it's a 3 times 1 minus 1, and 3 times 1 plus 2. So it's a 3 minus 1 is 2, 3 plus 2 is 5, it's 10. The right hand side is the 3 times 1 cubed plus 6 times 1 squared plus 1 is 10. So a of 1 is true. Left side is equal to right side. A of 1 is true. Okay, and next, assume that a of n is true for some n greater than or equal to 1. Okay, a of n is true for some n. Then let's check the next one for n plus 1. For n plus 1, the left hand side, okay, left hand side is sigma k from 1 to n plus 1, 3k minus 1, 3k plus 2. This is left hand side. You just change this to be n plus 1. And it's equal to k from 1 to n plus 1. So we separately write the final term. For k equal to n plus 1, you get 3 times n plus 1 minus 1. 3 times n plus 1 plus 2. Right? Can you see it clearly? Okay. Yeah. Okay, and then by the assumption a of n is true, it means this sigma is equal to this symbol. It's a 3n cubed plus 6n squared and plus n. And the final thing, let's simplify it. It is 3n plus 3 minus 1 plus 2. 3n plus 3 plus 2 is plus 5. Okay, let's continue the simplification. So it's 3n times 3n, 9n squared. 3n times 5, 15n. 2 times 3n, 6n. 2 times 5 is 10. So here it's a 15n squared. 1, 16, 22n. and plus 10. This is our left hand side. Okay, then let's check the right hand side. Right hand side for n equal for the n plus 1, you will get 3n plus 1 cubed plus 6n plus 1 squared and plus n plus 1. So your problem is to expand it. Let's try to expand it. Okay, so n plus 1 cubed is n cubed plus 3n squared plus 3n plus 1. N plus 1 squared, n squared plus 2n plus 1. Okay, so it's 3n cubed plus 9n squared plus 9n plus 3 plus 6n squared plus 12n plus 6 plus n plus 1. So 3n cubed, 9, 6, 15, 9, 10, 22, 3 plus 6, 9 plus 1 is 10. See, the left hand side, right hand side are equal. So a of n plus 1 is true. In this whole process, when you try to prove a of n plus 1, you do use your assumption a of n is true here. In this step, you do use this condition. It means from a of n is true, you get a of n plus 1 is true. Then by the principle of the mathematical induction, by the principle of mathematical induction, a of n is true for all natural number n. For all natural number n. Okay, so this is an example. The example. So mathematical induction is a very, very useful strategy, especially when your statement depends on the natural numbers. Okay. Next, we're going to show that the natural numbers and the integers, they are closed under addition and multiplication. Okay, so we're going to prove that if n and m belong to the natural numbers, or respectively belong to the integers, then n plus m and n times m belong to natural numbers, or respectively belongs to the integer set. Okay. Let's see. We're trying to ignore some common sense. We're trying to actually build up the common sense. Why our common sense is correct. For an integer, there are three cases. N is 0, n is a natural number, or negative n is a natural number. Right? For arbitrary integers, it belongs to one of those three situations, one and only one of those situations. So it suffices to prove the statement for the set of natural numbers only. If we can prove it for the natural numbers, then by this classification of integers, we can directly get it. Okay, so now what we are going to show? We are going to show given n belongs to the natural numbers, then n plus m and n times m belong to the set of natural numbers for all m belongs to natural numbers. Okay, so you add them. You add two numbers together. When we do that, we fix one and let the other one change. Okay, so see here we fix n in n. We fix n in n. Consider a set A is defined by the following: m is n belongs to the natural numbers, and m plus m is still a natural number. Okay, it's still a natural number. Okay, we're going to show that this set A is a set of whole natural numbers. N is here. M will change. We know that n belongs to n, then n plus 1 also belongs to n. This is one of the property we had right after the introduction of natural numbers. Okay, so it's one of the property. Your next neighbor also belongs to the natural numbers. Okay, so 1 belongs to A, belongs to this set A. Suppose element m belongs to A. Suppose m belongs to A. It means n plus m belongs to the integer. Okay, n plus m belongs to the integer. Then for m plus 1, I don't know if m plus 1 belongs to A or not. M plus 1. For m plus 1, how do we test it belongs to A or not? We just try to check n plus m plus 1. N plus parenthesis m plus 1. It is equal to n plus m and then plus 1 by the associativity. N plus m by the condition belongs to n, and plus 1 also belongs to n. Okay, so you see here, this time we use this condition assumption: m belongs to A, then m plus 1 also belongs to A, then m plus 1 belongs to A. First, 1 belongs to A. Second, from m belongs to A, belonging to A, we know that m plus 1 belongs to A. Then by the principle of mathematical induction, all n belongs to A. If all the natural numbers belongs to A, then what we get? We get A has to be the set of whole natural numbers. set A is a whole natural number. So n plus m, this addition is closed. Addition is closed in the natural number, set of natural numbers. Right? Addition is closed in the set of natural numbers. Now let's talk about the multiplication, the closure of the multiplication. How do we get the closure of multiplication? So this is set A. Now let's consider another set B, set of natural numbers such that n times m belongs to the natural number. Now same thing. So first, n times 1 is equal to n belongs to n. So 1 belongs to B, belongs to the set B. B of 1 is correct. Suppose m belongs to B. We know n times m belongs to the integer, set of natural numbers, set of natural numbers. N times m belongs to the set of natural numbers. Then for m plus 1. For m plus 1, we want to know if it belongs to B or not. We check n times m plus 1. N times m plus 1 is nm plus n. We know that n times m belongs to n belongs to n, and the addition is closed. We just show that addition is closed, so it belongs to n. Okay, so the proof of the second part, the proof of the multiplication, depend on the proof of the addition. Okay, so by the principle of mathematical induction, and m belongs to B for all m from the set of natural numbers. Every element in the natural number belongs to B. B is equal to the set of natural numbers, and the multiplication is closed. In the set of natural numbers, multiplication is closed. So we show that. Right? Okay, so this is the proof for the closeness of addition and multiplication for natural numbers and integers. Another example, a useful example, is to prove some property of the binomial theorem, or the related problem of the binomial theorem. What is a binomial? You have the binary power. You want to expand it. If you discuss the coefficients, you have the so-called binomial theorem. The coefficient of a plus b to nth power is the so-called Pascal's triangle. Pascal's triangle. This is a well-known triangle. Right? You can write more and more. The pattern is that every two adjacent numbers, the sum will be the number in the next line. The sum of every two adjacent number is the number in the next line. Okay, you always get this. And the left and right side is contains just one, number 1. This is so-called the Pascal's triangle. And all those numbers have some binomial coefficient writing. So we have, first, we define 0 choose 0 as 1. And then we define n choose k. This is definition, the meaning of definition, to be n factorial over k factorial times n minus k factorial, right? It's a binomial coefficient. Binomial coefficient. Okay, so this is line 0. Zeroth line. This is the first line and second. So this is value of n. N is a 1, n is 0, n is a 3, n is a 4, n is a 5. So every row you have 1, 2, 3, 4. Every position 0, 1, 2, 3, 4. You see, this is a 1, so let me rewrite it. It looks like 0, 0, 1, 0, 1, 1, 2, 0, 2, 1, and 2, 2. I read the, well, let me, no, sorry. You write the 1, 0, 1, 1. Yeah, this is the right order. 2, 0, 2, 1, 2, 2, 3, 0, 3, 1, 3, 2, 3, 3. So top is the row number, and you can continue this. Okay, and the formula is n factorial over k factorial times n minus k factorial. Okay, and the property we have is this. You see, we're trying to say that the sum of these two terms is the next one. So that's the lemma. What is the lemma? Lemma says, you see, here you have nth row, choose nth row, the k position, and its previous position, nth row, k minus 1's position. It is equal to n plus 1's row, k position. The next one, you see, this is second position. This is also second position. It's also second position. Okay, so we are going to prove this formula. This formula works for n, k in the set of natural numbers, and 1 less than or equal to k less than or equal to n. K is between 1 and n. Well, this one, we just directly calculate the factorial computation. Remember, what is a factorial? Factorial just means the product. The product of the integers. 1 times 2 times 3 times 4. Okay. Let's see. N choose k is n factorial, k factorial, n minus k factorial. N choose k minus 1, n factorial, k minus 1 factorial, n minus k plus 1 factorial. Okay? They both have the numerator n factorial. And first one, it becomes k factorial, n minus k factorial, plus here k minus 1 factorial, n minus k plus 1 factorial. Here this k minus 1 factorial also appears here. The k factorial is k minus 1 factorial times k. Right? So this one can be written as a k factorial and times k. So correct? So we factor out k minus 1 factorial here. And next, this term and this term, this one is n minus k plus 1, it's additional one, so it's n minus k plus 1 factorial is n minus k plus 1 times n minus k factorial. So this, you have n minus k factorial. So let's factor out n minus k factorial. So you get 1 over k plus n minus k plus 1. It's like this. Correct? Well, let's just continue the computation. It's not that crazy, but just tedious. Be careful. You find the common denominator, it's k n minus k plus 1. Then you get n minus k plus 1 plus k minus k plus k cancelled. You have n plus 1. N plus 1 composed with combined with n factorial is n plus 1 factorial. And k join this to k minus 1 is a k factorial. And this term joined to n minus k factorial is n minus k plus 1 factorial. And this is exactly n plus 1 choose k. See? Let me write this way. Move this 1 to the front. It's n plus 1 minus k. N plus 1 and k. Okay, so this is the end. I do it possibly too fast. If you don't understand it, try to compute by yourself and try to manipulate those factorial often. Okay? Okay, now with the help of this binomial coefficient, we can prove the binomial theorem. The binomial theorem says if a, b are real numbers and n is a natural number, then a plus b to nth power is equal to sigma k from 0 to n choose k, a to power n minus k, b to power k. Okay, a to power n minus k, b to power k. We're going to prove it. In the proof, we use the principle of mathematical induction. Okay, let's see the proof. So, the formula is true for n equal to 1. How do we know the formula is true for n equal to 1? The left hand side, n is a 1, a plus b to first power is just a plus b. The right hand side, sigma k from 0 to 1, 1 choose k, and a 1 minus k and bk. Remember that's here's n is 1. So 1, k is 0. So 1 choose 0. K is 0, it's a. B to 0 is a 1, you don't have it. 1, k is a 1, 1 choose 1. A to the power of 0, b to the power 1. A 1 choose 0 and 1 choose 1, they are both number 1 based on the formula we compute. Remember that. Keep in mind 0 factorial is 0. Okay, so this is a plus b. So you just do the computation, you will see they equal to each other. We cannot say trivially, but you really don't see a lot of computation. Okay, now assume that the formula is true for n, for some n, from the set of natural numbers. Then we are going to consider n plus 1. N plus 1. Okay, how do we consider it? So first we write a plus b to nth power, and then times a plus b. Just get an extra factor. Okay, then this one, we can apply this binomial theorem because we assume the formula is correct. So we will get sigma k from 0 to n choose k, a n minus k, and b k, a plus b. Right? So it's just like this. And then we're going to do product. So this one times a plus this one times b. So this sigma times a. Times a, you move this a into sigma, you get n minus k plus 1. N minus k plus 1. Okay? N minus k plus 1. I just distribute this a into each of the summands. And the sigma k from 0 to n choose k, a to the power n minus k. And you want to do the sigma with b, product sigma with b, you distribute b into the b part. It's a b to power k plus 1. So this plus 1 and this plus 1 come from a and b separately. All right? Now let's try to list them. Let's try to do some computation, okay? It's like this. So we first list this. It is let's make it longer. So it's n choose k equal to 0. K equal to 0, so it's n choose 0. Then you will have, what do you have? Yeah, you have a to power n plus 1. K is 0, b disappear. There's no b. The next, n choose 1. A to the k is 1. K is 1 is n minus 1 plus 1 is n. And then you have b to power 1. And n choose 2. A n minus 1 b squared. The last one, k is equal to n. So n choose n. And k is n. You have a to n minus n plus 1 is a. And b to n. Okay, so that's the whole thing about the first sigma. Second sigma. When k is 1, k is 0. When k is 0, n choose 0. N choose 0. A to n minus 0 is just still n. So a n b. So that's why I see I put it here because these two terms are like terms. You do not put it in the first place. You do not put this term in the first place. Okay? And then continue. When k is 1, n choose 1, a n minus 1, and b squared. When k is n minus 1, k is n minus 1, this is 1, and this is n. n minus 1 plus 1 is n. And when k is n, k is n, a disappears, you will have n plus 1. Okay, so this is the writing. You just write, expand those two sigmas, but in the alternating, not alternating, shift it one position. Now let's check. Let's check the formula we just proved. What is the formula? You see, nk minus 1. So here, n1, n0. Then you add these two terms together. So first one, this one, you just copy it. The sigma, the sum of those two coefficients is n plus 1, 1. You see how do you apply it? It's nk minus 1, n1, n0. It's a 1 minus 1. So you're going to add 1 for the row and choose the bigger number. So it's a n b. Here n2, n1 is n plus 1, n2, a n minus 1, b squared. And this row, this column is n plus 1, n, a, b, n, and plus n, n, a, b, n plus 1. Okay? So in this step, you do the addition of the coefficient for each column. All right? And then, okay, this is equal. Then next, n choose 0. You will see that for whatever integer n choose 0 is always 1. Always 1 for any integer. Natural number, not the integer. For any natural number, this is always 1. So here, instead of writing n choose 0, I'm going to write n plus 1 choose 0. Okay. Here, there's no reason behind it. It's just because of the comparison of values. It's not from the formula, because all such numbers are equal to 1. And then n choose 1, n plus 1 choose 1. And here, n plus 1 choose n. And final one, n choose n. You will also see that n choose n is also equal to 1 for every natural number n. So this is actually the left side. They're always 1. The second one is actually the right side. It's always 1. Because it's always 1, it doesn't matter what natural number you choose. So let's pick up n plus 1, n plus 1. All right? So that's not difficult, but complex writing. Try to understand this setting. And this final stuff is exactly the sigma k from 0 to n plus 1 choose k, a, n plus 1 minus k, and b k. You examine this. This is exactly the sigma. And this is the right-hand side. This is the right-hand side. So we start from the left-hand side, we get the right-hand side for n plus 1. In this proof, we do use the assumption the formula works for the integer, a natural number n. Okay, so this by the principle of mathematical induction the binomial theorem. The theorem is true for all n in the natural numbers. Okay, so this is the complete proof of the binomial theorem. It depends on a careful expansion of two sigmas and organize them nicely and do the column addition of coefficients. Okay, so all these are the examples of a principle of mathematical induction. So there are several exercises in this part. Okay, so try to do these exercise. This is on page, let me see, on page 17. On page 17, try to do them. They are not difficult. You just practice the principle of mathematical induction. That's it. Okay, we're going to finish this video and start another one for the next section. Okay, thank you.